Welcome to Talk Tensors. I want you to start off today by doing a really quick mental exercise.
Okay.
Just regarding the whole concept of translation. Imagine you were trying to translate this highly complex, nuanced piece of literature.
Like a modernist poem or something.
Yeah, exactly. Say English to French. You have to capture the syntax, the tone, the underlying cultural context, and the implied meaning.
Which is incredibly difficult.
It is. But computationally and linguistically, we have tools for that, right? We have dictionaries, grammatical rule sets.
We have a structural understanding of how discrete symbols map to other discrete symbols.
Right. Now, I want you to imagine doing that exact same translation process, but stripping away the discrete semantic symbols entirely.
Oh, boy.
Yeah. Working with pure high-dimensional visual data.
Just raw pixels.
Exactly. How do you computationally translate a sparse, simple line drawing into a photorealistic image of a shoe?
Or taking a photograph of a daytime street scene and flawlessly translating it into a nighttime scene.
Yes. Maintaining all the complex global illumination changes, the artificial light sources.
The geometric structures.
All of it. Because you aren't mapping words to words anymore. You are mapping pixels to pixels.
Yeah.
Millions of them simultaneously.
It's a staggering amount of data.
And for a very long time in the history of computer science and machine learning, this was a universal and often just an insurmountable challenge.
It really was one of the defining bottlenecks of the field. And what is so conceptually fascinating here is that the human visual cortex performs this kind of conditional visual translation effortlessly.
Right, instantaneously.
Yeah. If I show you a completely desaturated black and white photograph of a lush forest, your brain can instantly hallucinate what the green leaves, the brown tree trunks, the blue sky likely looked like in reality.
Because you project your prior understanding of the world onto that sparse data.
Exactly. If I show you a really crude preliminary sketch of a handbag, you can immediately imagine the texture of the leather.
The shiny metal buckles.
The volumetric depth. But teaching a machine learning algorithm to do this, to look at a semantic label map, which is essentially just a tensor of flat, color-coded blocks.
Where an integer value just says, this block is a car.
Right, and this block is a road. Trying to translate that sparse matrix into a hyper-realistic photograph of a city street, that requires an understanding of textures and lighting that traditional algorithms simply did not possess.
And that framing brings us directly to the mission statement for today's deep dive. We are focusing all our attention on a classic, profoundly seminal machine learning paper.
A really foundational one.
Yeah. It is officially titled Image-to-Image Translation with Conditional Adversarial Networks. But if you've spent any time in the computer vision or graphics community, you likely know this research by a different name.
The Pix2Pix paper.
Exactly. Widely known by its open source codebase, Pix2Pix. Our goal today is to rigorously break down how this single piece of research proposed a general-purpose algorithmic framework that fundamentally altered the field.
It changed the entire paradigm.
It really did. It moved us away from specialized algorithms and toward generalized, learned objective functions. But to truly appreciate the magnitude of this breakthrough, we have to look at the before times.
The historical context is crucial here. We need to look at the era just prior to the widespread adoption of conditional generative adversarial networks, or CGANs.
Right. What was the state of the art like back then?
It was incredibly fragmented, highly specialized. Researchers were treating every single image translation task as a completely isolated problem domain.
So requiring bespoke machinery for every little thing.
Exactly. If a research team wanted to colorize a black and white photo, they had to build a specific hand-engineered pipeline just for colorization.
And if another team wanted to do super resolution,
they built a completely different pipeline. In painting damaged photos, another separate architecture entirely. They relied on these computationally expensive mathematical frameworks.
It was a very artisanal era of machine learning.
Very handcrafted. You had entire academic departments spending months or years just trying to design the perfect mathematical loss function for one narrow visual task.
Which brings up the absolute crux of training any convolutional neural network, right? The objective function.
Yeah.
The loss function.
Scorecard.
Yeah, the scorecard. The network updates its weights via backpropagation by trying to minimize this specific mathematical metric. But this reliance on hand-engineered loss functions led to a massive philosophical hurdle.
The King Midas problem.
The King Midas problem. The authors of the paper bring this up, and it is such an apt analogy.
It perfectly describes the optimization landscape of deep learning. King Midas wished everything he touched would turn to gold.
Sounds like a great high-level goal.
Right, until he tries to eat his food or hug his family and turns them into solid metal. CNNs operate exactly like King Midas. They are ruthless mathematical optimizers.
They will literally, unapologetically minimize whatever specific loss function you define for them.
Without any broader common sense. If your mathematical equation has a loophole, the network will exploit it to lower its error rate.
Even if the output is visually completely useless to a human observer, you have to be incredibly careful what you wish for.
So careful.
Let's ground this in the actual mathematics they were struggling with. Say you take a naive approach to training a network to colorize a photo.
Okay.
You tell the network, predict the color values, and your loss function is the Euclidean distance between your predicted RGB pixels and the exact ground truth RGB pixels.
Standard L2 loss, or L1 loss, which is the absolute difference, the Manhattan distance.
Exactly. On paper, minimizing the geometric distance between the fake image and the real image sounds perfectly reasonable. Make the numbers match.
But what actually happens to the optimization landscape when you minimize L1 or L2 on a complex visual task?
You get mud.
You inevitably end up with a fundamentally blurry, grayish, muddy output.
Because of the statistical properties of uncertainty. Right.
Precisely. The mapping from sketch to photo is rarely deterministic. It is highly multimodal. Imagine the network is looking at a black and white photo of a jacket.
Well,
Based on the grayscale context, that jacket could plausibly be vibrant red, or it could be bright green. Both exist in the training data.
so the network is uncertain.
Very. And because L2 squares the error and L1 minimizes absolute error, the absolute safest mathematical strategy for the network is to not commit.
Don't pick red, don't pick green.
Right. It predicts the mathematical average, the median of all plausible colors. It hedges its bets to minimize the expected distance to any possible ground truth.
And the visual result of averaging bright red and bright green is a dull, desaturated, grayish-brown mess.
A completely muddy image.
And this statistical averaging phenomenon doesn't just ruin colors, it destroys high-frequency structural details, too.
Absolutely. It ruins spatial resolution. If the AI is even slightly uncertain whether a crisp, sharp edge like a brick on a wall should be at pixel A or pixel B,
It panics.
it compromises. To minimize the error, it just smears a faint, blurry edge across both pixel A and pixel B. It is structurally terrified of making a bold, sharp prediction in the wrong location.
Because being off by 1 pixel incurs a massive mathematical penalty under traditional loss functions.
Exactly. It's the ultimate mathematical compromise. The gradient descent curve looks fantastic, the score is low, but to a human eye, the image looks completely out of focus and synthetic.
Which brings us to the core thesis of this paper, the singular intellectual leap that made Pix2Pix a paradigm shift.
The researchers asked a conceptually brilliant question.
Instead of hand engineering a hopelessly complex loss function to micromanage the network pixel by pixel,
What if we just specify a high-level conceptual goal,
make the output indistinguishable from reality?
and then mathematically empower the network to learn its own loss function dynamically to achieve that goal?
The theoretical elegance of that is just astounding. And practically, they did this using conditional generative adversarial networks, GANs.
Right. Our listeners are likely familiar with the base concept of a GAN, the minimax game between two models.
The generator making the images, and the discriminator acting as the critic.
Guessing real or fake. But here, the generator's loss function is dynamic. It's determined by the gradients backpropagated from the discriminator.
It's an evolutionary arms race. And because blurry, grayish images look obviously fake to the discriminator, the generator has to abandon those safe averages.
It is mathematically forced to push its outputs into the high-frequency, vibrant spaces just to survive the game.
But let's clarify the conditional part of the CGAN,
Yeah.
because that's the crucial differentiator here.
Yes. In a standard GAN, the generator takes random noise and produces, say, a random face. The discriminator just asks, is this a real face?
But we don't want just any face or any shoe. We want the specific shoe from the input sketch.
Exactly. So both the generator and the discriminator observe the input image. They are conditioned on it.
The discriminator isn't just asking, does this look like a real photo? It's asking, does this look like a real photo? A and D. Is it the exact correct realization of this specific input sketch?
It evaluates realism and alignment simultaneously.
And that transition to an adaptive, learned loss conditioned on the input is what made this a general purpose framework.
The discriminator learns what reality looks like entirely based on whatever paired data set you feed it.
So you could use the exact same code base to turn day into night or sketches into photos. You just swap the training data.
It democratized image translation. You didn't need a PhD in advanced optimization to write a bespoke loss function anymore.
Let's transition into the architecture because the specific way they design these networks is brilliant. Let's start with the generator, the UNet bottleneck.
Right. To understand why they used a UNet, we have to dissect the standard encoder-decoder architecture that everyone else was using at the time.
And understand why it was failing so badly at high-frequency generation. Walk us through a traditional encoder-decoder.
Okay, let's assume you have an input image, say a 256 by 256 pixel image. The encoder passes this through sequential convolutional layers.
Downsampling it.
Yes, downsampling the spatial resolution, cutting the dimensions in half step by step while increasing the feature channels. It's compressing the high-resolution spatial data down to extract the deep semantic meaning.
Until it hits the bottleneck.
The deepest layer, where that original large image might be reduced to a tiny 1x1 or 4x4 spatial grid, a highly condensed semantic vector.
And then the decoder takes over.
Right. It ingests that tiny bottleneck representation and applies transposed convolutions, progressively upsampling it back out to a full 256 by 256 image.
Which makes sense conceptually if you just need to know, is there a dog in this photo?
For classification, it's fine.
But for image translation, it's a catastrophic flaw. All the information must flow through that narrow bottleneck.
Every single pixel in detail.
Think about it. If you're colorizing a photo, the input image already has perfect, crisp edges. The exact coordinates of every leaf on a tree.
Every wrinkle on a face.
Why would you mathematically mandate that the network compress all those exact coordinates down into a tiny 4x4 bottleneck, destroying the spatial alignment, just to force the decoder to blindly try to rebuild those edges from scratch?
It is computationally absurd. It's entirely inefficient. For these tasks, the precise spatial location of edges is shared perfectly between the input and the output.
So squeezing it through the bottleneck leads to severe structural degradation.
Soft, misaligned boundaries.
So the authors abandoned the standard encoder-decoder.
They adopted the UNet architecture.
And the defining feature of the UNet is skip connections. Let's explain those in plain English for our listeners.
Structurally, a skip connection is a direct wiring shortcut across the network.
Literally shuttling information from one side to the other.
Exactly. From a specific layer on the encoder side, directly across, completely bypassing the deep central bottleneck and feeding it into the mirror layer on the decoder side.
So layer 1 of the encoder wires directly to the final layer of the decoder.
Layer 2 to the second to last layer, and so on. It physically forms the shape of a capital U.
They don't just add the values together, right?
No, they physically concatenate them along the channel dimension. So the decoder layers suddenly have simultaneous access to two different streams of information.
The deep semantic info coming up from the bottleneck.
Which says, this region is metallic.
And the raw, uncorrupted, high-resolution structural info from the early layers via the skip connection.
Which says, exactly here are the sharp boundary lines of the metal object.
It's like using tracing paper.
That's a perfect analogy.
Right. If you're coloring a complex comic book cover with a standard bottleneck network, it's like staring at the line art, locking it in a drawer, and trying to redraw it from memory.
You'll remember the layout, but you'll fail to align the intricate lines.
But a UNet with skip connections is just tracing paper. You don't memorize the outline. You keep your eye directly on the original lines right under your pen while you color.
The transparency of the tracing paper allows the low-level reality to shine right through to the final output. It's an exquisitely elegant solution to spatial alignment.
And they proved it with ablation studies, didn't they?
Yes. When they severed the skip connections, reverting to a standard encoder-decoder, the outputs were visually soft and spatially misaligned.
The high-frequency boundaries were gone.
But the moment they plugged the skip connections back in, everything snapped into perfect alignment. It was non-negotiable.
Okay, so the generator is beautifully passing these high-resolution details across the network. But now we have to talk about the critic, the discriminator.
The other half of the game.
Right. If L1 loss is already forcing the generator to get the macroscopic layout correct, doesn't a massive adversarial loss create a huge balancing issue?
It could, but that leads to the deliberate division of labor based on spatial frequencies.
The math here is really cool. The objective function is the conditional adversarial loss plus the traditional L1 loss multiplied by a weight, lambda.
They found setting lambda to 100 gave the optimal gradient balance, heavily weighting the L1 loss to prioritize macro-level accuracy.
Because L1 loss and GAN loss handle different visual frequencies completely differently.
Exactly. High frequencies dictate rapid changes, sharp edges, crispness, local textures. L1 is notoriously terrible at that.
But it's great at low frequencies.
Yes. The overarching structure. L1 forces the constraint that the top of this image should be blue sky, the bottom should be gray road.
It anchors the big picture. It just fails at the texture of the asphalt.
So if L1 is robustly handling the broad, low-frequency picture, it's computationally redundant for the discriminator to evaluate the entire high-resolution canvas at once.
It doesn't need to look at the whole sky to know if the clouds look real.
Right. And that realization is the genesis of their second major innovation, the patchogen.
Instead of the discriminator ingesting the entire image and outputting a single real or fake score, it acts like a sliding magnifying glass.
It restricts its receptive field to local n by n patches. Specifically, 70 by 70 pixels worked optimally.
So it looks at a tiny square and asks, does this 70 by 70 patch of brick wall look structurally real?
Then it slides over, looks at the next patch and asks the same thing, generating a 2D matrix of probability scores, which are then averaged together.
And technically speaking, this models the image as a Markov random field.
Yes. It mathematically enforces the assumption that pixels separated by more than a patch diameter are conditionally independent.
Meaning, to know if tree bark looks real, I don't need to look at a car parked 3 blocks away in the background of the image.
Precisely. It assumes local independence. The patchogen abandons global evaluation and becomes a highly specialized, localized style and texture loss function.
Which is brilliant for engineering efficiency.
Massive benefits, far fewer parameters. It runs vastly faster during training.
And because it's just a sliding filter, you can train it on small 256 by 256 images.
But at test time, you can feed it a massive 4K resolution image.
And it just happily slides its little magnifying glass across the whole thing, enforcing crisp textures everywhere, independent of the image size.
It's an exquisitely elegant synthesis of regression and adversarial learning.
It really is beautifully balanced. But I want to pivot slightly because the authors admitted to a really fascinating, almost philosophical dilemma in the paper.
Ah, the noise dilemma.
The illusion of stochasticity. Generative networks are supposed to map a random noise vector, usually called ZIA, to an output, creating variation.
That is the mathematical ideal. If I give it a sketch of a shoe, it shouldn't output the exact same brown leather shoe every single time.
Right. Depending on the random noise, it should give me a red canvas shoe or a black suede sneaker. It should model the full entropy of the real world.
But the practical reality of gradient descent diverges sharply from that theory. The generator has a stubborn refusal to use the noise.
The authors fed Gaussian noise straight into the UNet, and the network just completely ignored it.
It shut the noise out entirely.
Why does that happen? Why would an AI actively ignore a perfectly valid input?
You have to look at what the network is incentivized to do. Its overriding goal is to minimize its combined loss function, stay close to the L1 ground truth, and fool the discriminator.
And the input image, the sketch, has all the reliable information needed to get a low L1 error.
Exactly. But the random noise vector is chaotic. It's uncorrelated. To the optimization algorithm, the noise isn't a tool for creative variation. It's a hostile distraction.
It makes minimizing the exact mathematical distance harder.
So during backpropagation, the weights associated with the noise input literally get pushed to zero. The network severs the connection and says, I don't need this random chaos. I'm just going to copy the reliable input image.
It's like an exhausted student taking an open book test. They have the textbook right there. Why would they roll a pair of chaotic dice to guess the answer?
They wouldn't. They just copy the safe answer from the book. It's a classic example of mode collapse.
So they were faced with a stubborn, deterministic network. They had to engineer a workaround to physically force it to be random.
Their solution was to use dropout. Monte Carlo dropout?
Randomly turning off neurons.
Right. Usually you only do that during training to prevent overfitting, but here they utilized it at both training and test time.
So during inference, internal pathways are just randomly shutting down as the signal propagates.
You're injecting noise directly into the physical architecture of the network. The generator can't ignore the noise if the noise is its own internal circuitry misfiring.
But even with this heavy-handed workaround, the authors admitted they only saw minor stochasticity.
Very localized variations, a slightly different shadow here, a subtly different brick texture there.
It wasn't wildly changing the color palette. Which leads to a really provocative question for the listener. Why is it so incredibly hard to force a neural network to be random when it has a perfectly good input image to copy from?
Capturing the full multimodal variation remained a deeply unsolved open question. It highlights the tension between gradient descent's desire for certainty and our desire for creative variance.
Speaking of color schemes and certainty, let's talk about the experiments, the empirical validation. Because they didn't just test this on one simple toy dataset.
They wanted to irrefutably establish that this was a general-purpose tool.
The variety is insane. Cityscapes dataset turning flat ladle maps into high-def photos of German streets.
Facades dataset turning geometric labels into realistic building fronts.
Google Maps into aerial satellite photos, black and white to color, edges to shoes, day to night.
It was a massive undertaking, but it brings up a fundamental evaluation problem. How do you scientifically prove an image looks real?
Right. If you're predicting a house price, you just check the dollar difference. But visual realism is a subjective human experience.
Traditional metrics like per pixel error are useless here. A perfectly realistic image that is shifted slightly to the left might have a terrible pixel error score.
While a blurry gray median image scores better mathematically.
Exactly. So to solve this evaluation crisis, they relied directly on human visual perception using Amazon Mechanical Turk.
I love this methodology. The AMT real versus fake flash tests, a high-speed digital Turing test for the human visual cortex.
The Turkers were presented with an image for exactly 1 single second.
Just 1,000 milliseconds. Then it vanished.
And they had to guess, real photograph or synthetic generated image.
And the data from these tests is so telling. Take the map to aerial photo task, when they used only the traditional L1 loss.
Those blurry images fooled the humans a mere 2.8% of the time.
Instant failure. But when they evaluated the full Pix2Pix CGN combo,
it fooled them 18.9% of the time.
From 2.8 to almost 19%. Nearly 1 in 5 times, a human looking at an AI satellite texture for a full second genuinely believed it was a real photo from space.
It's a massive leap in perceptual realism. But human evaluation is expensive, and we suffer from cognitive biases and fatigue.
So they needed a more objective, reproducible benchmark. And they used this clever pseudo-metric called the FCN score.
A really elegant way to computationally verify structural integrity.
Right, so you generate a fake street scene from a label map. How do you know it's structurally sound without a human eye? You feed that fake photo into a completely independent, off-the-shelf classifier.
Like an FCN8's network, one that has already been exhaustively trained to recognize cars and roads in real life.
If the generative network did its job, the classifier should be able to detect the visual signatures of the fake cars and buildings hidden in the pixels.
You are essentially using one AI to grade the homework of another AI. And as expected, the CGN framework scored significantly higher on detecting these objects than the L1 baselines.
Which perfectly leads into what is absolutely my favorite insight from the whole paper, the colorfulness phenomenon.
It's a huge aha moment for understanding adversarial loss.
We talked about how L1 loss minimizes error by choosing the median, the safe average, making things grayish-brown. But they didn't just state this, they quantified it.
They plotted the marginal distributions over the output color values using the lab color space.
And the decision to use lab space instead of standard RGB is important here, right?
Yes, lab space is perceptually uniform. Mathematical distance in lab correlates much closer to human color perception.
And the visual charts they provided are striking. The real ground truth photographs have a wide, varied color distribution, massive spikes for highly vibrant, saturated colors.
But the output of the network trained only on L1 loss. The distribution is incredibly narrow, tightly clustered right in the dead center around the dull grays and browns.
The network is mathematically terrified of making a bold, saturated color choice.
Because guessing bright red and being wrong incurs a massive L1 distance penalty.
But the CGN objective completely rewrites that optimization landscape. The patch chain critic looks at that safe, statistically average grayish coat and says, I've never seen this color in the real data. Real coats are either vibrant red or dark black. This gray is statistically improbable. It's obviously fake.
The adversarial loss realizes that the mathematical median is a glaring red flag for synthesis.
Yes, it explicitly forces the generator to commit. It pushes the output distribution to match the true marginal ground truth distribution.
It can no longer safely whisper a pale, low-confidence green. The gradients demand it confidently output a highly vibrant, realistic green.
Because vibrant colors are what actually exist in the real world. The critic literally pulls the artist completely out of their mathematical safe zone.
It's brilliant algorithmic design.
It really is. Now, as we look at the broader implications, let's talk about the legacy, the limitations, and the sheer community impact of this paper.
The cultural reaction was phenomenal.
Because the authors made a highly consequential decision. They open sourced the entire Pix2Pix code base.
Originally written in Torch, they just put the raw computational tools and training loops out there for anyone to download.
And it caught fire across the internet. It proved their thesis that this was a general commodity tool.
Developers, artists, and hobbyists started scraping their own bizarre data sets.
The community creations were legendary. Do you remember the hashtag edges to caps trend?
Oh, absolutely. Bizarrely popular and slightly terrifying.
People would draw these structurally chaotic, abstract line sketches of shapes, and the network would bravely try to texture them with photorealistic cat fur and eyeballs.
Just horrible, many-eyed, furry blobs. But it perfectly demonstrated the robustness of the patch-gen texture mapping.
It really did. And you had palette generation tools, or taking MS Paint sketches and translating them into fully rendered, volumetrically lit Pokemon.
And it moved beyond memes into serious interactive art. Memo Acton's piece, Learning to See, Gloomy Sunday.
Tell us about that one.
He used a webcam to feed a live visual feed of mundane objects on his desk, a tangled cord, a cloth into a U-net trained on crashing ocean waves or raging fire.
And it dynamically translated his desktop reality into these fluid elemental landscapes in real time.
It was a profound showcase of the temporal stability and creative potential of the framework.
But to be fully rigorous, we have to address the limitations. The authors were very upfront about their architectural blind spots.
Yes. While GANs are undeniable magic for human-facing perceptual realism, they are not the optimal tool for every domain.
Specifically, purely deterministic vision tasks.
Right. Suppose you want to do the exact reverse of what we've been talking about. Input a photo and predict the discrete semantic labels, outlining exactly where the cars and trees are.
Standard semantic segmentation.
For that kind of one-to-one mapping, adding the CGN adversarial loss was completely unnecessary. It actually performed slightly worse and introduced gradient instability.
If there's only one mathematically correct answer like, this pixel is definitively part of a car, you don't need a complex critic to enforce realism.
It doesn't need to look realistic, it just needs to be accurate. Plain L1 regression achieved superior scores.
Don't use an adversarial sledgehammer to push in a regression thumbtack.
Exactly. CGNs are vital when the output space is multimodal and you need a critic to force a choice, not for strict discrete categorization.
But that limitation doesn't diminish its legacy. Almost every modern diffusion model or advanced neural style transfer architecture owes a massive conceptual debt to this paper.
The ripple effects are still driving the state of the art today.
Absolutely undeniable.
Okay.
We have thoroughly unpacked the methodology. It is time to transition into our novel notions segment.
Our favorite part. As always, a quick disclaimer for our listeners. The ideas discussed in this segment are highly speculative, theoretical extrapolations for entertainment purposes only. They have not been empirically tested.
With that disclaimer firmly in place, based on the power of the patch can and the U-net, I am pitching you two outlandish but architecturally plausible research ideas.
Let's hear them.
Idea number 1, temporal patch GANs for generalized life simulation.
Court temporal, applying this to time series data.
Exactly. We know the 2D patch GAN enforces a Markov random field, assuming spatial independence beyond an n-pixel radius. What if we build a 4-dimensional temporal patch GAN?
Applying the conditional independence assumption to the temporal dimension. Fascinating. How would the topology work?
Imagine conditioning the network on incredibly sparse personal or physical data, say a few scattered health metrics or financial snapshots from a bank account over a decade.
So the input tensor is a very sparse representation of reality.
Right. Uses a temporal U-net. The deep layers process the overarching macro trajectory of those 10 years. But the 1D temporal skip connections shuttle the exact raw data points directly across to anchor the temporal reality.
And the critic.
The temporal patch GAN doesn't look at the whole decade at once. It slides a narrow window, say a 3-month patch, across the generated timeline. It penalizes that specific localized window to ensure the day-to-day, high-frequency texture of the simulated events is statistically realistic.
So you're generating hyper-realistic alternate life histories by matching the localized temporal distribution of behavior, extrapolating the textured spaces between sparse data points.
Yes.
What's a practical first experiment for this that avoids the chaos of human behavior?
Localized weather system failures. Fluid dynamics. Say a hurricane wipes out a sensor station, and you lose 3 weeks of barometric pressure and wind shear data.
Oh, I see. You use the temporal patch gen to seamlessly in-paint the lost time series tensor.
Exactly. The L1 loss anchors it to the sensor readings before and after the blackout. But the temporal patch gen ensures the hour-to-hour microfluctuations synthesized during the blackout exhibit the chaotic, high-frequency texture of a real storm.
Instead of just a smooth, unrealistic L1 straight line interpolation between 2 points.
Exactly. It applies the texture loss to the dimension of time.
That is entirely logically consistent. Massive implications for climate modeling or satellite telemetry feeds.
Okay, idea 2. Pushing conditional translation to the biological limit. Cross-modal UNets for neural translation.
Changing modalities entirely.
We've been talking pixel to pixel. I'm talking translating raw fMRI brainwaves directly into visual fields, thought to photo.
How do you architecturally bypass the semantic gap between a noisy 3D brain scan and high-frequency RGB pixels?
You rely on the biological topography of the human visual cortex. Neuroscience shows the primary visual cortex maintains a strict top rexical map of what you're seeing. You use a cross-modal UNet. The fMRI volumetric data goes into the encoder. The bottleneck extracts the deep semantic, meaning the person is looking at a face.
And the stick connections.
They're wired to map the localized regions of the V1 and V2 visual cortex data directly to the corresponding spatial pixel regions on the output canvas, completely bypassing the bottleneck.
Shuttling the raw neurological edge detections straight to the image generator.
And the patch scan.
fMRI scans are noisy. If you just use L1 loss against a ground truth image, you'll get a blurry gray mess. But the patch gen critic is trained on millions of natural high-res human visual fields.
It slides across the generated output and ruthlessly forces it to look like a valid, crisp human field of vision.
Yes. The CGN forces the generator to resolve those blurry fMRI signals into sharp visual textures to survive the critic, while the LN loss grounds the spatial layout to the physical brain scan.
The generative AI would literally be hallucinating the high-frequency visual details that the fMRI resolution can't physically capture, but hallucinating them in a statistically consistent way. You are synthetically developing the high-definition photograph of a human thought.
It's terrifying, brilliant, and conceptually sound.
And that concept of hallucinating realism brings us to our final provocative thought for the listener to mull over.
Lay it on us.
We spent this entire time analyzing how a neural network can learn its own objective function, defining reality based on the feedback of a critic.
Right.
If we project this forward, as these discriminator networks get exponentially more complex with vastly deeper layers, at what point does the critic's internal learned representation of reality become more important than the actual physical ground truth training data?
If the AI is literally generating the fundamental rules of what constitutes visual realism,
Are we still studying the real world? Or are we just blindly studying the deeply complex mathematical imagination of the critic network?
it's a deeply fitting epistemological question. The line between capturing the statistical distribution of reality and actively creating a new one is getting blurrier with every gradient update.
Thank you for joining us on this deep dive into learned loss functions. Keep questioning the objective functions governing the systems in your own life. We'll see you next time.